So I'm recording this because like NASA probably does know like, and I mean they're really smart, but they don't know maybe what I meant when it comes down to the whole like making lasers. And it's like lasers. Do you know how hard it? I mean they're so inefficient. And they have to be so. This is really far away. Meanwhile, you can't see nothing. This is good. So, anyways. But it's like, no, but you have natural light around you from the fucking star we orbit called the sun, right? Not to mention the reflective wave propagations of planets, right? And then it's like, no, we're not even fully done because, like, if you know about radio wave and constructive interferences, not to mention the fact that we don't need really anything other than light, right? We just need light. Light, not all the same, right? But it's also the fact that if you point it and you know what you're doing and you can propagate that wave, so it's like, here, I'll pulse it here, I have a steady state, and I pulse a laser, it likes to slowly with a grid all come together as a constant stream, like a laser, right? But that means you have to do the pointy point as, the world spins, and then there's the orbital thing, right? So, and then same thing with others, and then there's gravitational lensing bullshit, and then, other static charge differences, the neutron density, blah, blah, which you don't probably need to calculate, but if it's there, it's there. I mean, it is pretty fucking far away, so, like, you might need to. Anyways, point is, as a result of it propagating, that means you have to constantly go from all the way as far as you can, and then work your way back, and then eventually it goes. All right, so we calculate for all these given types of influential variables. We then manage to be able to more easily define this given light headed towards a given direction. Now, as it gets closer to us, then what we do is we end up getting this thing called more control. More control then allows for us to aim it and point it at the telescopes that we want. Simple stuff. It's, rather simple when you explain it that way. But other people, it's like, it's a lot of work. I'm gonna have to scribble fucking moon runes on this fucking sheet of paper with like all this fucking pluses and parentheses, I'm sure. I don't wanna. I don't wanna do that. I don't wanna fucking do that. I'm like, it's like your job, isn't it? To do math or something? Like, you got hired to do things like that, right? Yeah, I mean, it seems like it shouldn't be that bad. But, like, you also have big computers. They can't lie about being super big. They take up huge rooms. So, I think they'll help. So there's that. But it's like, no. Behold, I'm looking at the wall over here. Imagine, if you will, there was stuff there. I can see it in my mind, because it's the imagination thing. But, whatever. So, anyways. Imagine, if you will, somehow magically. Don't have brains that can imagine somehow. I don't know how that works. I have Amphantasia. I can still do this. I don't get it. Anyways, you had calculated some of these orbits already and the reflective properties of these given planets, and that you absolutely pretty much knew more or less the most as you could of the LIGO levels of gravitational influential data and the noise data that you account for to look for these large things anyways, which then can be used as data for you to do this thing. Now, just as there's a light behind me, two over there, right? Well, that's steady state, right? But it's like you can also steady state a constant laser and then steady state pulses, right? And we know about light wave interference getting us into the attoseconds, right? Well, we're not looking for attoseconds or any of that. We're looking for keeping a propagational wave consistent. That's called phasing. I call it the Lemke principle phasor array. It's on my YouTube channel. Anyways, that allows for you to create a tunnel, which allows for light that's likely to be there, meaning radio wave, natural, all those stuff, to be on certain angles and superpositional, types. It allows for it to effectively interfere in such a way that it will just naturally propagate and amplify. But we're not looking for it to just amplify light shine that way. We need it not interfere on the way back. Now, that one's the resonant frequency stuff. right? So it's like light, if you know about the wavelength that you're trying to get to move backwards through the given wavelength that's heading that direction, that's like an alternating current, a resonance. All right, so if you know anything about resonance, then it's like, yeah, okay, so well, it'll dump a little bit of its light into that, all right? And of course, it allows for some light to go back that way. It has other light that'll go the other way. Simple stuff, right? But the way that happens means you need to make sure that every single time you're constantly maintaining an input of energy into this given system, which is light, right? You have to constantly maintain the light heading that direction and heading backwards. So it's like, if it's heading this way and it's going to propagate and it's going to eventually diffuse and everything else, that means you have to angle it multiple times to create moments, chunks of interference types. And so it'll go from this, big to, and so it's a big undulational wave of a sort inside, right? And it starts looking a lot more like a resonance pump, to put it mildly, right? But what it means, though, is that you get a wonderful, nice little wave propagation that is less interfered and maintains that given whatever light that was in that given area, its type. That's a good way to put it. Like, it's, not just luminance. It's not going to do superposition. It can't do superposition. You might be able to get that done, though. That's a little bit more difficult, though. Angular, right? Like, angular light. You know how much you're going to put into, in terms of luminance for the light, for its wavelength, for blue shift. Okay? Which then means it's like, well, knowing that this input of variable that we are, and that could be there, then means we can denoise that and know from that given area, from this given sensor data, we can then allow for ourselves to know what the result of possible light that was there is. Right? Now that's with, like, not the far infrared and whatnot, because of course we're blue shifting it up, right? But it also means that we have a very narrow, tiny window. That's what we have. We have a little tiny window. That's it. It's a telescope lens is essentially what we're creating out of light, right? But that also means it's like, it takes a little bit. It takes about a week to get that kind of shit done, for what it's worth, because we're talking like, what is it, like 7,000 miles away or not miles, years of orbit, right? So it's like, that's a really far distance, right? Like, not small astronomical units, right? So if that's the case, then it's like, well, yeah, no, I mean, you kind of chunk it in a different type of way. Like, instead of a light year, you're going to be doing light, like, picoseconds or some shit, whatever you can get. You know what I mean? So, and after a point, you have to remember, like, we're taking light that's already from around that area and then adding it back in. So, like, that's the curvature. So we're talking like an hourglass figure now to the given light that's propagating that way to that way. We create a tube, but then you have an hourglass figure that goes towards a given multitude of points, and so we have to input our informational energy and light energy and so on to sustain that, right? But that also means we get a dark section elsewhere. See, we're interfering in such a way that that light will go away. Not the greatest thing if you needed that, but we don't. We don't care. We're looking for fucking Planet 9. Okay, like, we don't care. So who cares? You know what I mean? What does it matter, right? I don't see a big deal, personally. That's me. Maybe other people need it. I don't think that's the case. But, we all have to then do the whole international astrometer thing of like, look, guys, we're going to do this thing. You don't need to look over there, okay? Okay, like in this small section of a zoom in, and it's like this one little area. Don't look over there. That's not a good thing. Don't look there. You have this area over here, all over there. You don't have any of this area though. Like, don't look over there. It's gone. Yeah, that kind of thing, right? So it's like, that's gone now. Remember that. except it's not. But like that's kind of the weird part. Like a lot of people don't really understand that part. It's like, why does it go somewhere? It doesn't went into the freaking light coming back at you. You know, like really, I can already hear that. Like, you know what I mean? Not like in my head, but like how people are. I have to fucking argue with a bunch of people that really don't understand any of it. So it's the light went somewhere. It's good. There's a big blooming of radio waves at very low end that might be there. And of course, the unfortunate part is, as a result of that light propagating, it will continue and eventually diffuse outwards and no longer look like it is, which will be a telltale sign to anything that's trying to look at us. If it was in with a few hundred, I mean, it's light years. We're talking years. I really don't think anything's close enough. I mean, we'd have seen something. So I don't think I have to worry about aliens and whatever. Yeah. Aliens. But point is, it's like, well, it's doable. It's just a bit different than you might expect. It's like we're going to be using like both orbits, but also gravitational lensing of our planets because we're going to get real close for that light, the laser light, right? And we're also going to be using natural light, and that's amplitude of light, effectively, as it curves at blue shifts, but it also takes in extra light as it also has its own sort of gravity well. And then there's reflectivity thing, you know, which happens to help with that sort of situation. And depending on what we're talking about, how close it is and how far away it is, you know, that allows for you to continue propagating light. Now, we're talking about bending light only a slight amount. I mean, even the moon isn't that much, right? Even Jupiter can't really do much, okay? But it's really mostly the reflectivity light and the fact that light interfering with itself will bend itself as a result. It's acting like a lens. That's constructive and destructive. So like it's destructive towards its path, but it's constructive in the path that it now takes. That kind of thing. Sort of situation. But like you have to do that right. And it's like, well, yeah. Well, there's magnetic interference. So give me a second, okay? Give me a, you know, with tube TVs. You remember the tubies? The TV of the tubes. I don't know. I'm old. I don't know about you, but I'm old. I remember when they were a thing, and pew, and then we shaped it, right? Well, guess what? That means light is doing that already. We have planets that already have magnetospheres, right? Same thing with the star we orbit, all right? So it's like we can actually use that to more and more influence light behind us and then moving forward, not just towards the thing, but from behind, right? What that means is that it becomes more and more like a continuous lensing of light. It becomes more laminaristic, which is apparently not coherent. That's more of a lens versus coherent, which is much more of a laser, right? They are all the same wavelength. I don't care about that wavelength. It's actually going to be several different wavelengths that have to do that, right? Which means we do have laser, but we also do have steady state lens, and then we do have propagation of regular light. Now we don't need nearly as strong of light to do what it is I'm proposing, right? We don't need huge, massive lasers anymore. We need to point them the right place. We need to have the right wavelength, and we need them to be large enough and still quite powerful, but, you know, not nearly as much, which is a good thing. And that also means we have to pulse regular steady state like a, you know, bulb of like a flashlight, right? On. Which effectively means we have to learn how to destructively and constructively, but also just have regular antenna wavelength microwave kind of stuff that's pointed in that area that we can constructively interfere over time and distance, which allows for us to get that proper wavelength. Now, of course, that means we also have to, you know, corral it back into place, but that's what a lensing is doing for the constructive and destructive interferences that we're talking about. Okay? Now, that also means we have to be very, very careful about both gravity, orbital mechanics, spins of the bodies that we're talking about for the planets, but also the magnetospheres themselves. And if we do it right and do it very well, we might be able to just point in that direction and get a much better result than if we didn't. You know what I mean? So, on the other side, the flip side, it's also like, well, if it happened to be such that a lot of these, near Oort cloud, extreme, or those things, right, happen to be able to gravitationally influence with a gravitational resonant frequency. Okay, and then we happen to have other celestial bodies within inside of our astronomical backyard, which is our galaxy. Okay, such that they were able to magnify and amplify their given types and really kind of also focus their gravity fields and propagation of waves, then they might actually account for a Planet 9. Which is the kind of problem. It's like, while we don't know necessarily all of that, we also don't know that we don't have that also as a possibility. And it's really based upon how it is that might occur, which means I could really feasibly, with the math, kind of make that work. Sort of a problem for astronomers. You know what I mean? Like, oh, I really like this light idea, but what if it was just a bunch of gravity that happened to work together the right way? Well, I wanted the light stuff. Can we do the light stuff? Hey, what about this light? Where are you going? Where are you going? Where are you going with the light stuff? I like that idea. Meanwhile, my butt also goes like, it's very theoretically possible, very feasible, very hypothetically, very like the gravitational influence, especially over that amount of time and how it propagates through our solar system, along with other solar systems within our galaxy and all the rest. And so it's possible that because they're that far away from the sun, it then means that. And as they have to travel inwards, they're more likely to be influenced by those gravitational wave pushes and have reflectivity or curvatures, which isn't really reflectivity. But that's because of as it has a gravity, then it's a curvature thing. So it curves back towards anyways. It's much less, but if it hits the right constructive interference of gravity waves, then... and all the right things, then it should do it. I don't know what to tell you, man. So, it's feasible, but of course we're playing with numbers. And of course we have some things that are there, but then we don't have any of the things before the things that we started having. Meaning LIGO is not ubiquitous past this point in time. It's like, oh, I know, it's right here, we made it, and that's great information. And what about before? Well, but what? We don't know. That's kind of the problem. You know what I mean? And so that means it turns into, well, there are possible resonant frequencies that could possibly do that. And constructive interferences. And so that might be the thing. Of course, we're talking about a big, long orbit, so it's like, how does it do this? Well, propagation of gravitational waves from Mercury, Venus, Earth, Mars, and so on are going to mix. That's a faster to a slower to a slower to a slower as they travel along in their orbit, but also as they spin, which spin is a type of tearing, sort of that kind of frequency, right? And then you have a bigger, longer wave. And if you know anything about attosecond lasers, then you know it's a medium, short, and long wave. And wouldn't you know it, there are many of those throughout many different types of solar systems, including ours. So it's very possible that we might have one of those things going on. And now, I don't know if that necessarily changes how those work to the degree that we get a body of mass and orbit the equivalent of this, but it's possible in my mind that it could resultively do that. So, one's a big amount of calculations that I can definitely guarantee you can write the numbers to fit it. And the other is a big, cool fucking light show. And then maybe we can just find out. And maybe we even have LIGO detection from afar. From afar. Imagine there's a word there, from afar. Anyways, imagination. Anyways, see ya.